So today's talk is about learning, and it's about machine learning as well, but I decided to make it slightly more general because this is just one of these fun meetings where you get to talk about why you research in this area. I'm going to follow the model of Robert Britson, which is to try to rather point out what has inspired me to be doing this type of work. So the first thing is because throughout life, the best moments have always involved learning. When we were learning to walk, that was a lot of fun. When we were learning to swim, and not just we as humans, all animals learn. Learning to snowboard and so on. As you can see, the guy's having a lot of fun. Learning to program. No, that's not me. And even learning to deal with a situation like being at the bar and trying to find a mate. You eventually learn to do it better. Learning is fun. But also, it can be associated with very tough times during our lives. We learn a lot through relationships and the failure of relationships. We know, or some of us already know what it's like to deal with death. And you learn a lot about yourself and about life and so on when you're faced with those things, or when you face accidents, or when you face big threats in life. Learning is critical. There are lots of things that we learn that are less high level and conscious than what I mentioned, like just learning to see. When we are born, we already have a lot of capacity there to see. Like we can follow very badly, but slowly we can follow a finger. We have color detectors, but we don't seem to have very good feature detectors, like for shape and so on. So a big part of vision is learned. And I will mention an experiment that makes that clear. We learn to talk. I think most of that's pretty controversial. The structures that allow us to talk might be there in place, but at some stage we learned. And even if the structures are in place, there was an evolutionary process that is, in a sense, a way of learning. We learn abstractions, which are necessary for language. We learn what a function is. The concept of a function, a relation, is not actually obvious. So when our students are struggling in programming, that's because they're actually learning new ways of abstract, new ways of thought that they didn't have before. Children, let's actually do this experiment with you guys. If I show you these two images, this image on the left and this image here on the right, what would you say is in common between the two images? Someone. Let's say mouse chasing. Okay, it says what's in common is that someone is chasing someone. Does everyone agree? Cats. Cats. Okay. Not to put yourself in the spot, but 3-year-olds, when they show these two images, not these specific two images, but there's been experiments similar to this, they will go, kitty, kitty. Whereas 5-year-olds will go, chase, chase. Okay? It's an abstraction. They've learned this concept of chasing, and this concept takes two entities, and you can have a function now that's this much more complex relation between two entities. We also learn to make moral judgments. Little children, 3-year-olds and so on, are not very good at making moral judgments because they cannot entertain the possibility that you have beliefs in your head. And there's beautiful experiments that show that. In fact, that point to, with using fMRI, to parts of the brain that are involved in maintaining beliefs about other people. And Rebecca Sachs at MIT has this beautiful, beautiful TED Talk, which I recommend to everyone to watch, where she actually has these experiments with children, and she shows that some of them cannot make moral judgments, and then it's only really at the age of 9 where they can actually start being able to understand whether someone's at fault or not. Because if you cannot believe that someone else could have beliefs in their head, it's hard to believe whether they thought they were doing the right thing or the wrong thing. In general, what's driven me to learning is this wish to understand the world, to understand my own condition, the universe, what this whole thing is about. One of my favorite books ever when I was a child is this book called Watership Down. It's about these little bunnies that get killed and their environment is destroyed and so on. But the one little bunny, Hazel, he's the guy in the middle here. Simon and Garfunkel had this Bright Eyes movie about Hazel. It's a little bunny trying to understand the world and trying to come up with not just the immediate world, but the mystical world. The LRI, I think is called their version of God for bunnies. And it's always that amazes me. It's we trying to understand that which is big. When I play with my dog and I'm like, Picasso, do you want to go to the beach? And he's like looking at me, like his head moves, trying to understand. He'll never be able to understand me. And it's that same thing with humans. We're like trying to understand things that our mind will never be able to understand. And yet we keep forcing that boundary. And that is truly what I find fascinating about learning. One of my favorite quotes is one due to Albert Einstein. When he was asked what it's like to do research, he says well, it's like playing on the beach, like looking for shells on the beach. And honestly, doing a lot of this research for me has been like that, always trying to find interesting things as you walk down the beach. That's scientific curiosity, but it's a curiosity, again, that is not only scientific. All of us have it in different aspects of our lives. Animals have it, like these dogs here. Even mold, even this, what's it called, this type of mold? It has a name, Byron.
Slime mold, I think.
Slime mold. Slime mold is pretty clever because it's a mold, but it can solve mazes. It can do planning. It can do things that anyone would think is super high-level cognition. So even the most basic creatures, survivors of evolution, just like us, are capable of doing this. All creatures are capable of doing these amazing things. But this desire to understand, it's to understand our condition in the world and to try to understand knowledge and so on. And some have corrupted that. I did learning also because I love mathematics. And I think mathematics and abstraction is essential to be able to do science. And I think we ought to do a lot more for our students to do mathematics. Jobs out there require that people know math. You don't get past an interview with Google unless you know your math. And we ought to be true to that. If we don't give our students enough math, they will not be able to succeed in their careers, and they will never be able to reach that higher level thinking that comes with abstraction. In terms of learning, like more practically, why we're using machines, I'm interested in things like eventually having vehicles that are autonomous. So there's an example here, which I love. It's due to Peter Bill and Ang Green. We have actually, taught a helicopter how to fly, and it's pretty successful. It flies upside down. It does all sorts of maneuvers that most human pilots are not capable of doing. All vehicles should be eventually automatic. I don't think humans should be allowed to drive cars because 40,000 die every year in North America in car accidents. Most of them young people. 100 and something die every year in India. And it's just barbaric. I mean, compare those figures with what we call the ultimate barbaric act of our time, the Twin Towers going down. That's only 2,000 people. We're talking 40,000 a year. it's really barbaric to let people drive. So one day there'll be good cars that will take you, or people will have good sense of designing public transport in cities. But if not, then we need to improve that. Anomaly detection, disaster prevention, as this is something that's becoming more and more important, monitoring the environment, being able to detect whether a disaster is going to happen by taking all the data that we can gather from sensor networks and so on, satellites, and being able to react timely. Energy prediction is becoming very hot these days as well. And these are technologies for which governments now are pumping a lot of money. These days, in fact, if you're going to start a company in these sectors, green tech, energy prediction, the government will be happy to give you the money for you to start. Entertainment is another area where machine learning has played a big role, especially in Microsoft. And then, of course, machine learning is very much embedded in a lot of the biology research in terms of designing better drugs, in terms of doing better diagnosis, prognosis of cancer, and so on. And it's become key in dealing with the explosion of data. So if you know machine learning, you likely will get a job at Google or Yahoo or Microsoft because they're desperate to have good people that can handle lots of data. So when should we use machine learning? I think the first part where you would need these tools is when you deal with a situation where you just cannot have a human there. In this example, I said Mars because you can't have a human in Mars right now. So if you're going to have a robot there, the robot has to have the capacity to learn whether it's wheelless type or whether it's just an alien that's attacking it or something. You know, it has to be able to react to the environment, and it has to be able to plan a path and so on, because it's not capable. It cannot communicate with Earth in a timely manner. Learning is also important because it seems to be a big part of how we learn to sense the world, to hear, to smell, to taste, to see. And for all these things, we cannot introspect. So we don't know how we see, we don't know how we smell. And as an example of this, what I'm showing you here is something called change blindness. And Ron Rensick has some beautiful videos on this. Most of you probably have seen this one, if it comes up. Let's try it out. Okay. So follow the instructions on this video up here. Alright, so who saw except David, because I know David's seen this video before. What changes did you see?
There was a woman in front of the shop there.
That's right. Did everyone see the woman in front of the shop disappearing? 2 people. What else?
The shop at the back, a woman or a man appeared.
Yes, that's right. So a lot of things changed. So in particular, notice that this building now is sort of pinkish. It has a sign. The doors here are brown. Somehow the wrought iron is broken. And there's doors here. This door is green. There's no people here. This was the original image. It changed before your eyes, and you truly believe you saw it, but you didn't. And that's to do with limitations of your buffer, and it's got to do with the fact how we see by doing saccades. Now that just makes the point that we don't understand how we see, I can show you that you're not seeing the way you think you're seeing. And so this lack of introspection does not allow us to take an approach where we go and design an eye that sees. But rather, we're going to have to go from the same data that human vision evolved, and from that data try to learn a model. So we will not be able to do it any other way. It also happens, it's also an interesting problem in choice making. We think we're making a choice, but we might not be making that choice. It's also useful because in a lot of settings, the signals keep changing over time. So if you're doing environmental monitoring, for example, you might have a particular device that might be drifting, or the environmental conditions of the lake that you're monitoring are changing over time. And it doesn't mean that a fault has appeared. It just means that there are external conditions, not all of which you can anticipate to model in advance. It's also useful when you need to deploy a technique for which you have to tune it to the user. Pretty much any web service these days. But the sort of classical example is speech recognition, where there's reasonably okay general speech recognition, but it's much better if you tune it to the user. So if you ask the user to please read a paragraph loud, then the system will adapt to the user and it will work a lot better. And of course, there are these domains where there's so much data that it's just impossible for us to comprehend in our heads, and so there we need to automatically deal with the data. When working at the search engine, and something I've done in the past, you should never rely on having humans doing anything. Always try to go for the full data and bring in machine learning. Otherwise, you'll just be wasting your time. Here's an interesting figure that appeared in The Economist last year. And it shows that the rate at which information is being created in the world. This is the rate at which it's being stored, which is huge. This is in exabytes. So we're dealing with this huge explosion of data, more than we can actually store, iPhones and so on. I'll give some of the examples. Again, an exabyte, just to revise this, is 2 to the 60 bytes. Wikipedia, if you had it uncompressed and the English version only, is about 112 gigabytes or 896 billion bits. This will be relevant to a discussion at the end of the talk. The human brain has 60,000 that many zero synapses and 100 that many zeros neurons. So note that the size of Wikipedia, uncompressed in bits, if you take each neuron to be a bit, is about the same. When we talk about later about neural models that people use, this will come to have a relevance. The point that I'm trying to make here is that it's only now, over the last, 10, 20 years, that we have the capacity to store as much data as a cat would store in its brain. So never before were we close to AI. Not sure if we are close now, but certainly not before. Here's an example of another example of where data is being produced, astronomic data, and this kind of gives you sort of a sense for it. That whenever a new telescope appears, just within a few years, more data is created by that telescope than ever before. So it's exploding exponentially. And of course, it's also the huge amount of data is also very common in the stock markets these days, where everything gets done electronically, and there one has to deal with lots of data, not only in terms of dealing with the big size, but also being able to deal with it efficiently, quickly. I think more and more we're going to move from the doctor that has your files and will not give you the files, and then you have to pay $60 to transfer the files from one office in Yalta to an office in Kitsilano. We're going to move away from that to an electronic information about your medical records, because that's a lot better for you and for the future and so on. There's certain privacy issues there, but one day we'll have information, well, this database already has it, information about, I don't know, mammograms all over the country, and from that you can actually do spatial statistics and find out why it is that, say, people in one particular state might be having more cancer than in another. Just to show you a sense of which data has been exploding, the Library of Congress has about 20 terabytes. AT&T phone calls that they record are now up to 323 terabytes. World of Warcraft is 1.3 petabytes. Avatar, 1 petabyte for the effect. Google processes 24 petabytes of data per day, so 1 petabyte an hour, but that's insignificant compared to YouTube. And this is where the future is. This is the game. For anyone with machine learning, is to be able to do video and understand from video. Because video is just exploding. And now that it's up on the iPhones and so on, the trend I think will continue. Of course, it's already doing intelligent machine learning for dealing with market data or reports or news or what people are saying, collaborative filtering, or even measures of sentiment, whether people are happy about the fact that there's protests in Cairo or not. All of this data is now being used by companies trading to do better, or by companies trying to sell products. I found this beautiful logo on the web. Note that eBay is a market data reseller, not an auction house. Because they have all the data about who buys what, for what price, what people are prepared to do in their auctions, and you can get a lot of data that will drive the markets from that. So with all this data come lots of opportunities in science, in even building more useful interfaces for paraplegic people. There's opportunities to do spatial statistics, like this sort of thing that Google already does, where you can find crimes in different areas, like Point Grey and so on. And with being able to find patterns, I think actually you eventually start moving toward knowing what knowledge is there in the data. And that I think will be essential in bringing people to the economy. In Halevi, Norvig, and Pereira have this beautiful paper where they talk about this explosion of data. And one of them mentions that in '67, a huge data set was like 1 million words. Nowadays, the standard data set, well, not nowadays, in 2006, had just got 1 million times bigger. And they mentioned two big successes on the web. One is speech recognition, one's machine translation. And what's common in these approaches is that there's lots of data. That's the first thing, and labeled data, because for each sentence in French there's a sentence somewhere in English. And with speech recognition, every time the Google phone doesn't understand you, you can correct it. And that data Google takes and updates its models. So there's this continuous learning every time the user is engaged. And one of the strategies that Google uses is memory. And the way memory works is as follows. Suppose you wanted to learn to translate from Spanish to French, Spanish to English. What you would do is very simple. You would get a bunch of sentence pairs. You would compute how often do words correspond to each other. So we know that I love appears here and here. So it must be then that U maps to 10. But you still can't resolve I love, but if you had more sentences, then you would be able to resolve, you would know which word maps to which word, which would allow you to do translation. Because you'd be able to build a probabilistic table of counts of how often some words translate to others. And then you basically would repeat these steps. And this is essentially something that we use in machine learning called the EM algorithm, which allows us to do translation. Very simple. But data is data, so if you have an algorithm, you can apply that algorithm to any other type of data. You could, for example, take an image, segment it, extract, segment words into nouns, and now you have again a translation problem. So we have lots of images with captions on the web and video and so on, but we don't know which object corresponds to what word. And you could then learn to classify parts of the image if you were to do that. Or you could do something very nice, like what Alyosha does at CMU, which is he cuts an image, and then if you have a large enough data set of images, you can actually fill in the image. But you need a lot of data. With few data, you can't do. So there's this whole thing that's driving machine learning, which is this explosion of data on the web. It really has created many opportunities. It also has led to all this speculation that we don't need any more sound probabilistic models and so on, let just the data speak. But that is actually something that's already been talked about before. It's non-parametric statistics, where you have simpler models that pay attention to the data. And it's well understood. And I'll come to that point soon in the next slide. Halaby, Norvig, and Pereira conclude by saying that they've solved the problem of getting people to give them data, and that's because people love to give data away in Facebook and so on. They've solved the problem of aggregating all that data and searching and so on. I claim maybe not, but they do a pretty good job at that. But there is this question, which is interpreting the content, and that's still not solved. And again, I think that's one of the big challenges for machine learning and probabilistic modeling. David Poole's been doing a lot of work on this. What is the probability of something actually truly happening, given all the evidence? Coming back to this question of having large data, it really goes down to basic knowledge. If you have a polynomial of degree 2, from which you can sample points, and then you use a polynomial of degree 1 to recover those points, then it's clear that you will never be able to recover the model perfectly. So the type of picture that I have is one where you have data that follows, say, this quadratic function, polynomial to degree. And so if you fit a line through that data, you'll always make an error. The model is just too simple. The truth is bigger than the model. And that's why sometimes we have models that just are incapable of modeling the data when we have a lot of, even if we have lots of data. If you have the right model, like a degree 2 model, then you'll get a nice fit to the model. And if you have a model that is really flexible, it will do a very bad job fitting the data, but if you get more and more and more and more data, the model will eventually provide a good fit. You will eventually constrain the model. Now, that's essentially what's happening in the web with very large data sets. It's just a question of having a lot of data. So you can use a model that's very flexible, in fact, so flexible that it eventually provides one basis function to take the point, you do something not parametric, and that's why it works. But good mathematical modeling, good statistical modeling is still what has to be used to understand what's happening now with large data sets in the web. There's another thing that's inspired me in my research, and it's neuroscience. And that's because, again, there are all these things for which we're very good at doing, but we don't know how to get machines to do them. And then one looks into neuroscience, hopefully for some insight. That doesn't pay off always, because neuroscience is a very, very big field with millions of papers on any topic, no matter how narrow you choose it. But it's also not very deep, in the sense that if you're interested in a particular topic, then a lot of people will say a lot of things about it, but there's nothing that is known for sure. Nonetheless, there is there are some interesting results that I will, some of which I'll point out today. This is also a good example of a lot of data. There's this site called brainmaps.org, where it's kind of like Google, like they say, they're the Google Earth for the brain. And you can actually go there and look at different slices of the brain and so on for different animals. Now the brain is interesting because unlike standard memory in a computer, it has this nice property. It's an associative memory. If you show something that kind of looks like what you want, you query it, you get that item back. There's a very good example of that, and need a subject for that. Can I volunteer you? You don't even need to stand. So I'm just going to ask you to say the alphabet loudly.
A, B, C, D,
Just
E, F, G, H,
backwards now.
G,
Oh no. Oh yeah, do it backward now from there.
D, C, D, A.
All right. So hardly to demonstrate with Tim because I need a speaker of English. How about you? Who is happy to volunteer their phone number? Say it to yourselves. I can say my phone number very quickly forward, 77823911190. Now if I try to say it backward, I need to think. 0, 9, 1, 1, in fact I kind of go back. Hang on, 0, 9, do this experiment yourself, just because what you've stored is a pattern in your head which has temporal order. You can't recall your phone backward. We learned sequential patterns. And same with the alphabet. In fact, I hear from David it was being used as a test for drunken driving because they'll ask people to say the alphabet backward. And people are really bad at saying the alphabet backward. They're very good at saying it forwardly. So here is, there's other things that we know about. There's been some amazing findings. Like, for example, there's neurons that will fire. This is the path of a rat walking around. And here there's a population of neurons that always fires at these periodic places. Okay, so in the brain, we have information that encodes exactly where we are in our orientation and so on. So I can close my eyes and I can walk around and I know I'm not going to hit the wall until more or less here. Okay, because we have that path integrator inside our head. So for people who do robotics and do slime and so on, these are the neural correlates for that. Another part of the brain that has inspired my research a lot over the last few years is vision. It's how we take an image from the world, pass it through. Here we're showing just one pathway, which is via LGN, and then mapped back to the visual cortex, area 17V1. And this is just one pathway. There's other pathways, but this one is kind of interesting for the following experiments. These gentlemen here, Hubel and Wiesel, did this experiment with an animal. Hubel and Wiesel, did they do it with a cat or with a monkey? I don't remember what their experiment was with.
Originally cat.
Some mammal, where they move a bar in different directions. And then they probe the neurons to measure whether they're firing or not. And what they find is that the neurons fire when you move a bar in one direction. Like when this bar moves from here to here, you get the neuron firing, tuck, 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 and it doesn't fire in the other direction. So neurons are selective to orientation. And in fact, people have sort of mapped this. And they, like for different orientations, there's a nice topographic map of how these cells in V1 are organized. And they're also organized by another dimension, which is location in the world. So if 2 points are close in the world, they will be close in the brain. And it's a combination of that and a combination of having a topographic representation. It really should be 3D, but the brain has optimized it to be plane. So we have all these filters. These are actually computed with the learning algorithm that I'll describe now. And it's important to do that because when we deal with text, text is like super easy because we know what the good features of text are, what the patterns are. The patterns are words, combinations of words. So it's very easy to extract a pattern. But often in machine learning, we need to figure out what the patterns are in the signals before we can make predictions. And so with images, it's very hard to think what elements of an image are enough to fully describe an image and allow me to make predictions, and do it in a way that is both storage and computationally efficient. And I mean, we're dealing with this huge video of the world. How do we handle it? So we have these, from images, we try to learn these same filters that correspond to these neurons in the brain. There's a model for doing that that's received a lot of attention recently, and over the last 4 years, pretty much most of my research has been about this. So the model basically takes images as inputs. So it has each of these units corresponds to a visible pixel, and each of these units, just in a similar way, sort of a caricature way of what happens in V1, gets mapped to a neuron that either fires depending what the image is. So each neuron will fire to a particular orientation in the world. What we want is we want to learn these models. We want to learn the same models that V1 have. We want to get these topographic maps that will allow us to take an image and quickly say what's in that image. And so here's an example. So what we would want is to take an image and be able to identify, okay, it has a vertical bar, say, it has a small vertical bar, and so on. So it's a distributed coding of what the image is. If we have this type of pattern as well, the beautiful thing about this is binary, so we have a nice semantic hash for the image. And if we could have semantic hashes for YouTube, that would be amazing. If we could search video efficiently, we could solve a lot of interesting problems, as well as a lot of business problems. Like there's a lot of money, for example, in being able to detect copies in YouTube for copyright infringement. And the scale is so large that it's, unless we learn to extract good features like this, that we will be able to map into some sort of hash. It will be very hard otherwise. Now, how we're going to learn this is going to be based on sort of an ecological principle. We're dealing at the end of the day with NP-hard problems, so one needs to answer how do we manage to do that? Because the space of images is huge. Okay, so if I have binary pixels here and 16, I have 2 to the 16 possibilities of what this image could be about. Now, if you think of the million pixels that go into LGN that I'm seeing, I have well, not 2 to the million, but some sort of continuous number to the, say, 256 to the million. How do we handle that image? And how do we learn from that image? The answer is we don't look at the worst case. We only look at the things that actually happen to occur in the world. And that's why those strokes will arise, because the natural statistics of images are such that little edges and corners are much more common than any other pattern. So this is sort of the idea of what we want to do. From an image, we want to extract this binary vector. One interesting work that was done about 6 years ago in Toronto was the following. From an image, you learn this sort of the vector of features, in this case 2000. These are the sort of features. And then what Jeff Hinton and collaborators decided to do there was to then freeze these, and then learn the next level up, and the next level, and the next level. So this is sort of a hacky and greedy, but it actually works reasonably well. And it's quite amazing that you can code something down to 30 bits and then still be able to decode it. And in fact, if you had, like Jeff loves his examples of digits, if you have images of numbers from 0 to 9, you can actually code it all the way to 2 and get a very nice separation between them. Okay, so this is kind of one of the things that we love to do in machine learning, which is to do this dimensionality reduction. is also useful for visualization. People have taken this research further and tried to learn patterns that are more than just ages, and they're trying to learn things like faces, parts of cars, parts of faces, and so on. And here, maybe because there's some findings in neuroscience that seem to indicate that we can also, groups of neurons can fire for a particular face. So if I see David, that group of neurons will fire. I don't need to ever have to interpret that David has 2 eyes and so on. So eventually I build in my head neurons for most of the people I know. Those models can also model temporal aspects, where you could have something like an image at time t+1 and an image at time t. And if you do that, then you can also, by doing parameter estimation for these guys, you can learn filters that capture transformations. Like in this case, these filters are capturing translations, these filters are capturing rotations, these filters are capturing scale. So we learned the natural transformations that arise in the world. What Jeff then does, that I think is quite cute, is that he does the following. He trains the model with 2 of these images. Like he'll take, what is best if I draw it? He'll take something like a vertical bar, then a horizontal bar, and then from that he passes that information up, and he learns the units that fire. He then freezes these guys. So that's process 2. And then he presents another image here. So he'll present a 2. And then what happens, because the transformation's been frozen, is that it will do the corresponding transformation. So this is key, because we talked about analogy, going back to the cat, chase. Even though it's super simple, it's like an important step toward being able to actually learn these analogies. Analogy is very key to intelligence, and we actually don't know how analogy works yet, or how to model analogy well. I think this is kind of a promising area. Of course, if you do this for images, you can do it for video. One of my students has done that. And if you can do it for video, you can take gazes of an image and then be able to predict, to try to complete. Because if you know that, if you have a gaze and you know, for example here, that this is the head of the guy, and you need to know whether he's wearing Nike shoes and so on, because you can already do the prediction as to where the legs are, you can now move your eye here. So being able to predict the world helps you with doing things more intelligently. Now these models, although I motivated them from a neuroscience perspective, I could have motivated them completely differently. And I will do so to hammer this point as to why it's so important that we do teach more math to our students. If we take something like SAT, which is something most of our undergrads managed to get a degree without knowing, we all know, those of us who've encountered it before, that it's one of those beautiful problems for which you can very easily check whether something is satisfiable or not, but it's very hard to compute a solution, and we've even come up with nice words to describe that process. So here is a simple example where I have just 4 sentences, 4 implications. And if I just take its symbol, in this case actually theta 1, theta 2, 3, 4 should be all 1. That's from a previous slide. If you take its symbol, if it's a not, if the logical form is a not, you convert it to just a variable that's the opposite, and you just flip it, and if it's, you make it just be the variable b, and if it's the logical b, you transform it to 1 minus b, and then you can rename them, so you can call this x1, x2, and so on. You end up with exactly the same model that Jeff Hinton has. Okay, and this is something that's well known. It's an Ising model, and the models that we use to model brain or V1 are just these Ising models that have been used for a long time in physics to model, for example, whether a particle is in a position or not. Say, like in this case, on might be red, off might be blue. There's an important fact that is connected to this, and it's the second law second law of thermodynamics, which is a statistical statement that says if you have cold molecules and hot molecules, you have a chamber at high temperature, these molecules will be moving very quickly. If you open the door, we all know what happens. The temperature becomes the same in both. And that's essentially the second law that models it. But now let's consider the following. And that we have a guy called Maxwell's demon. And this guy looks at the particles, and every time it sees a particle coming very fast, it opens the door and lets it through. But if the particle comes slowly, it doesn't open the door. And then, voila, the little demon has violated the second law of thermodynamics. It's able to revert the process of how the universe is evolving. The key for this to happen is that this demon can actually see whether the particle is fast or not. Has information, in other words. And indeed, this demon changes the energy and the entropy, but it only does that because there's a relation that we know from statistical physics about information and physics. Information and energy. And so all these quantities, all this knowledge of physics, all the mathematical modeling from theory of computation and so on, they all are relevant to be able to do learning. And they all are relevant if you're going to go and try to work in YouTube. Now, to finish and demonstrate learning in humans, I love this particular example here of George Tenenbaum. So in this example, he's got 3 images of tufas. And now I'm going to use you guys in the audience and ask you to vote for who thinks the following is a tufa. How about this guy? How many people would say that it's a tufa? Put their hands up. How many people think it's not a tufa? Indifferent? What about this guy? How many people would say it is? 2.
I think everything's a tufa.
Who thinks it's not a tufa?
Right.
Okay, less people do. Who is indifferent? Who doesn't know? Okay. What about this guy here? Who thinks it's not a tufa? Okay, more people do. Okay, so very quickly, you jump to the conclusion of what a tufa is or not. So you learn what a tufa is, whatever a tufa might be. Someone told me actually once that it is actually something. I'm not sure of that. I have no idea what a tufa is. But what's interesting is we quickly learn. Learning is happening in this huge leap, what George called the inductive leap. Learning doesn't happen slowly. You don't need to see a million examples. You don't need to see all the data on the web to learn. Just a couple of examples and you learn. Key to it is that you're also seeing features. So you only have 3 labels. You don't need someone pointing at the data as to what data are. But the key to it is we can extract features quickly from these other data that will help us with it. Ian?
I should point out, I saw somewhere a paper that said that even if you don't show people what those things are, if you just start using particular words, they will associate them with certain features. So it's not just that you're learning from what you told us, it's that we already associate certain features.
Here you would already, if I showed you the next image without showing you this one, you would probably make the same judgments. But so there's another question then, and it's how did you still learn that quickly? From 3 examples, how can you learn so quickly? This is George's take on it. And it's So there's a group of people in machine learning that are worried about the web and big data sets, which is kind of what I've been conveying in this talk. There's another group that is looking at neuroscience for answers that will help, or for some computational principles that will help. And usually the actually interaction happens both ways. We help the neuroscientists a lot. And then there's another group that is trying to learn what Chomsky calls the universal grammars. It's more in the tradition of Bayesian statistics and the philosophical tradition. And it goes as follows. What you try to learn is a probabilistic model that will take you from the signal to some model of what's being said, in this case of language, to some type of model, in this case a particular grammar, to eventually, or tree, in this case a parse tree, to eventually be able to extract grammars and eventually have the grammars for language. So the idea is that you would learn a probabilistic model for which, if you have some data that you can talk about the data, but then you also need to learn as a hypothesis as to how the data might be organized, in this case a tree for species and properties. And then you also have to learn what is the general theory from which these models come from. If you have this higher level knowledge, if you already have this knowledge, if you have learned before, higher level knowledge as to the type of structures that arise in the world, dependencies, things being correlated, things being organized in a tree. These are all things we acquire in our childhood when we go to school and they tell us, well, you know, there's mammals and there's like felines and whatever the other categories, and then there's plants on this side and they're all beings and so on. So that's one possible data structure for data that we learn, and then we use that data structure over and over and over again, and that allows us to do new tasks more efficiently, allows us to learn more efficiently. So in essence, what we're learning here is in Bayesianism is the priors. Josh thinks you can learn, I don't know, maybe a handful of these structures, and you'll be able to deal with most of the things most of the ways people reason about data. But what's nice about having these Bayesian hierarchical models is that if you get a new species and your data is incomplete, you can use the model to predict what the remaining features for that species should be. You will have different models, but if you have proper probabilistic modeling, you'll also be able to figure out what's the probability of each model and be able to reach conclusions and so on. So what Josh has been doing, and also Stuart at Berkeley, is and David here, is to try to build actually these hierarchical probabilistic models that will have a much higher level of abstraction and will be able to deal with all sorts of problems in reasoning. I think that's what I am talking. And I think that's one of the very exciting ways in which it's going. And the languages are changing. I don't have a demo with me, but some of the languages that people are using now allow you to express if you have a good knowledge of probability, the way you could solve any problem that arises in practice is just by specifying in a very abstract way 3 probability distributions, and voila, your problem gets solved. You have clustered documents, or you've made predictions about energy and so on. Key to that is this increased abstraction and good management of probability. And that's the talk.
So you said 2 contradictory things. One is you need a lot of data to learn, and another is you can learn from just a couple of examples. Are they completely different learning algorithms, or is there, is there a way of unifying?
It's the same learning algorithms, in fact, but then you need these priors. You need to have learned the higher level models, the grammars and so on. Google has not learned the grammars. So they need a lot of data to be able to do any predictions. But if they had good sound models, they wouldn't need as much data. The problem is that learning such good sound models is very hard. But eventually they'll have to do it. Because if they want to compute what's the probability that Brad Pitt and Angelina Jolie are still in love based on all the tabloids that are on the web, they need to be able to aggregate data and actually figure out what's do the things that we do. What's the evidence? How sound is the evidence? How authoritative? And how likely is the fact to be true? So I don't think they're contradictory. It just depends how much data you have, depends on what structures of knowledge you have.
Often we talk about the need for labeled data to help with learning. In your Tula example, you showed 3 and called them Tulas, and said you could learn really quickly, but admitted you have no idea what people are learning because we have no idea what a Tula is. To me, it would be helpful if you had examples of things that weren't Tulas. So negative examples as well as positive examples, and how does that fit into a scheme of learning from labeled data?
True. So negative examples do help a lot. That's very true. But the part of learning that I should subscribe to believes that there should be no supervision. You should be able to learn without supervision, because most of what we learn throughout life did not involve someone telling us what to do or how to see, or we learn either by trying, by a process of reinforcement learning, or we learn in a way that's similar to what Jeff, like those models that I was doing of extracting features, all that is unsupervised. And so the idea is that if you can learn to extract features from the data without any supervisory signal, the features that I've extracted from the images that I've received while I lived in Canada are features that will help me if I move to Russia. So I learn a lot of features here, and from those features I can predict whether a classroom is friendly or not friendly. If I take those features to Russia, I can quickly use those features to retune my classifier to predict whether the classroom is friendly or not. I don't need to relearn features. And so right now the trend is really more in that sense, is to try to learn as much as possible in an unsupervised way, and then be able to transfer that knowledge to new tasks. So I personally think you should learn as much, that the real challenge is to learn in an unsupervised way.
But you're not arguing for the abolishment of all schooling.
Pardon?
You're not arguing for the abolishment of all schooling.
Of all schooling.
We learn everything on our own. We don't need to go to school.
No, actually, that's a real challenge as well. So in fact, there was a paper at ICML a few years ago where it's called curriculum development. It's a very cute paper, Joshua venture with it. I think it was Joshua's group, where indeed they tried to train one of these machines in that way. Learn simple things first, and then sort of like to try to have some other way of trying to design a curriculum so that this model will learn as much as possible. How do you design a curriculum so that this model learns a lot about images, or this student learns a lot about computer science? People have started exploring that. It's fascinating, but it's still very preliminary.
Purely unsupervised learning in nature, because when we are learning in nature, we are constantly doing things and getting feedback from the nature, and that feedback can be considered as kind of a supervisor to our learning.
Very true. There's a lot of feedback in nature. In particular, because we live in a dynamic environment, time is an amazing Time is an amazing supervisory signal. Because, my eyes are here, they've already moved 4 times in a second, and that information is sort of being stored, so I know my eye was here, then was here, so this is a supervisory signal. So indeed, there's a lot of supervision in that sense. The type of supervision that In a sense, I think the problem is, and Alex Smolik, who's a sort of big machine learning guy, and he's also voiced this, that it's hard often to make that distinction between what's supervised and what's unsupervised learning. But certainly what we should try to avoid is use this notion that we will take a huge database of something and we will label it by hand and then train a model in it. No, we need to look at the data and see how to find correlations in the data. So like temporal correlations, or if you're acting upon the world, then you can figure out what are the consequences to your actions, and you can use that to build a model of action, and so on. So there is a lot of supervision in nature, but the trick is to find out how that supervision happens. You should learn that, how is the supervision happening, as opposed to try to hard code it. That's a very good point.
Some point is that you learn from regular features, and then you went off and said you see a lot of edges, therefore you pick up edges first in your V1. But that's not. I mean, that might be actually true of V1, but that's not true of other parts of the cortex. Like for instance, you go from your area MT goes from being completely mature to almost full maturity in 2 months. And you don't see, I mean, as an infant, you don't see a lot of motion around you. I mean, it's mostly, I mean, unless you're born in a racing car or something. Well, I mean, but not as much, not to the extent that somehow your motion detectors would get trained first before your V2, for instance.
True.
I mean, why doesn't your V2? So somehow, I mean, my point is that word regular could be interpreted in 2 ways. One as in it appears regularly, and another way is that just the structures are regular in some sense because you have topographic maps in your brain somehow, and so on and so forth. And so anyway, I just object to this interpretation of the word regular as appearing on a regular basis. And hence, the conflation of machine learning and statistics.
So there's some structures that capture natural statistics. I think that's an argument that's made for V1. I think by far most of the brain is unknown. It's just a big piece of jelly that people are trying to figure out. The bits that we know are the bits that we're sort of trying to bobble. And we're born with a lot of this, like you mentioned, MT, a lot of motion detectors are there already. There's a lot of pathways. It's fairly complex and we know very little of it yet. I think we should cut.
Yep, thank you.